Welcome to the Explainer. Sometimes the biggest ideas in science are hiding in plain sight. Today, we're going to take something we've all experienced, a simple trip to the playground, and use it to unlock two of the most fundamental concepts in all of physics.
All right, so let's just dive right into our puzzle. It all kicks off with a totally normal scene, but one that's hiding a few really fascinating questions.
Take a look at this. It's just a playground, right? Seems pretty simple. But believe it or not, a physicist looks at this and sees a fantastic puzzle just waiting to be solved.
These are the questions we're going to dig into. How fast is a kid going to be at the bottom of the slide? Does it matter if they're bigger or smaller? And the big one, which slide is actually the fastest? To even begin to answer these, we first need to get a handle on a word we all think we know. And that word is work. You see, the way a physicist defines work is probably way different from how you and I use that word every single day.
Yeah, in physics, work has nothing to do with your job or your homework or how tired you feel. It's not about effort at all. It's about two things and two things only: force and movement.
Okay, so here's the absolute key. For work to happen, in the physics sense, two things must be true. First, you have to apply a force. Second, the object you're applying it to has to actually move. If there's no movement, there is no work. It's really that black and white.
And this is a perfect way to picture it. Let's say you lift 3 bags of wheat instead of just 1. Well, to do that, you're going to need 3 times the force, which means you do 3 times the work. It's a direct relationship. More force equals more work. And you guessed it, the same exact logic applies to distance. If you use the same amount of force, but you move that bag 3 times higher, you've done 3 times the work. Simple as that. So how do we measure all this? Well, we measure work in a special unit called the joule, named after James Prescott Joule, a scientist who did a ton of pioneering work on energy back in the 1800s.
Now, this is where it gets really interesting, because not all work is the same. It can actually be positive, negative, or even zero. And it all comes down to one simple thing: direction.
It really is all about which way things are going. If you push something and it moves in the same direction you're pushing, you're doing positive work. You're basically adding energy to it. But if you apply a force to slow something down, you're doing negative work. You're taking energy away.
Just picture a goalkeeper stopping a cannonball of a shot. The football is flying one way, right? But her hands apply a force in the exact opposite direction to bring it to a screeching halt.
In this example, what she's actually doing is negative 30 joules of work on the ball. She is literally pulling 30 joules of energy out of it to stop its motion. So we have positive and negative work. But what about those times you feel like you're working your tail off, but a physicist would say you're doing absolutely nothing? Well, that's where the idea of zero work comes in.
I mean, we've all done this, right? You push against a solid wall with all your strength. You're sweating, your muscles are burning, but the wall isn't moving an inch. In the language of physics, you have done exactly zero work on the wall anyway. Your muscles are definitely working, but you haven't changed the wall's situation one bit.
Okay, so we've been talking a lot about this thing called work. But what's the big deal? Why does it matter so much? Because, as it turns out, understanding work is the key. It's the secret password to understanding its much more famous twin, energy. It's such a simple definition, isn't it? Energy is just the capacity to do work. You can think of it like the currency of the universe. It's the stuff that allows things to happen. It's the potential to apply a force and make something move.
So when you do positive work on an object, like when you throw this cricket ball, what you're really doing is transferring energy into it. Now that ball, as it's flying through the air, possesses that energy. It has the capacity to do work on whatever it hits. In this case, sending those wickets flying.
And this, right here, is the master key. This connects everything we've been talking about. It's called the work-energy theorem, and it's a fundamental law of the universe. It simply states that the amount of work you put into an object is exactly equal to the change in energy you get out. They are two sides of the very same coin.
And you know what? There's a special name for the energy an object has just because it's moving. We call that kinetic energy. So the more positive work you do to get something moving faster, the more kinetic energy it gains.
Okay, we've got our tools. We understand work, positive, negative, and zero. We understand energy. And most importantly, we know how they're linked. So let's head back to that playground and finally solve our puzzle.
So here we are again. Same playground, same slides, but this time we're looking at it with brand new eyes. We're not just seeing kids having fun, we're seeing a physics laboratory in action.
Now we can see what's really going on. As a child goes down that slide, the force of gravity is doing positive work on them, constantly pulling them down. And all of that work gets converted into the energy of motion, into kinetic energy, making them go faster and faster and faster.
So, we're not going to crunch all the numbers here, but I'll leave you with this question. Using everything you now know about work and energy, how would you start to figure out which slide is fastest? The answer isn't just about which one is steepest. The real puzzle is which slide's shape allows gravity to do its work most efficiently to build up that speed. That's the real physics of fun, and now you've got the tools to start figuring it out.